Hi, welcome to today's talk on Newton's laws of motion. What are we learning? We're going to list each of Newton's three laws of motion, and then we're going to show how Newton's laws of motion explain the motion of objects. Our essential question: what do Newton's three laws of motion tell us about why objects move? First, a law is a universal law if it states that some kind of conditions, so far as are known, are always found together with certain other conditions. Let's take a look at Newton's first law of motion, the law of inertia. So, you've heard this before. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. Let's get a little deeper on that. First, the tendency of an object to continue in its original state of motion is called inertia. Mass is a measure of an object's resistance to a change in motion. The more mass something has, the more it resists a change in its motion. This is called inertial mass, and we'll look at gravitational mass a little bit later. Another way of saying Newton's first law of motion, or the law of inertia, is to say that an object's velocity is constant if the sum of the external forces is zero. Let's go back to our crash test dummies for an example of an object at rest that tends to stay at rest. Depending on the point of reference, this can also be an object in motion that tends to stay in motion. From the outside, the unbelted rear passenger is an object at rest tending to stay at rest. If we look from the inside of the cabin and pretend that the car is moving, we can see the unbelted rear seat passenger as an object in motion tending to stay in motion. An object at rest tending to stay at rest. An object in motion tending to stay in motion. For another example of inertia, in 1977, NASA launched the Voyager 1 and Voyager 2 spacecraft. These were the first visitors to the outer solar system. These were the first close-up views of Jupiter, Saturn, Uranus, and Neptune. These two spacecraft are also examples of inertia. They are objects in motion that tend to stay in motion. They are both so far from any other object that we can say that they have almost no external forces on them. They will continue traveling on these paths for all practical purposes ever. Space is incredibly empty. They have virtually no chance of ever hitting anything. For example, if, let's say, 1 inch is equal to 1 astronomical unit, which is the distance between the Sun and the Earth. The Voyagers are about 13 feet away from the Sun today. The nearest star, Proxima Centauri, at this scale would be, say, in Downey or Inglewood. It would take around 80,000 years for the Voyagers to get there, if they were pointed in that direction. The takeaway from this is that if the net force on an object is zero, like the Voyager 1 and the Voyager 2 spacecraft, they will continue to travel in their current direction at their current speed for, forever. Newton's first law explains what happens to an object when there are no net forces acting on it. The object either remains at rest or continues moving in a straight line at a constant speed. Newton's second law answers the question of what happens to an object that does have a net force acting on it. Imagine pushing a block of ice across a frictionless horizontal surface. When you exert some force on the object on the block, it moves with an acceleration of, say, 2 meters per second, or 2 meters per second squared. If you apply a force twice as large, or 2 times that F, you will get an acceleration that is twice as large, or 4 meters per second squared. Pushing 3 times as hard triples the acceleration, and so on. From these observations, we can conclude that the acceleration of an object is directly proportional to the net force acting on it. And here we can see it in our equation. The acceleration equals the net force, or the sum of the forces in newtons, divided by the mass in kilograms. Mass also affects acceleration. Let's say you push this block again with a certain amount of force and it accelerates at 2 meters per second squared. Then we stack an additional mass on top of that. We double the mass. Now our acceleration is half as much. Acceleration is inversely proportional to mass. Here we see it in this equation, where acceleration is the sum of the forces divided by the mass. If we double the mass, our acceleration is cut in half. As we saw before, if we double the force, we double the acceleration. Acceleration is inversely proportional to mass. It is directly proportional to force. We've talked about newtons before, but now let's define it. A newton is a kilogram meter per second squared. 1 newton of force will accelerate 1 kilogram by 1 meter per second squared. The conversion factor between newtons and pounds is 1 newton equals 0.225 pounds. And finally, let's take a look at Newton's third law. This is the law that has to do with action and reaction forces. Now imagine driving a nail into a block of wood. To accelerate the nail and drive it into the block, the hammer must exert a force on the nail. And here's the free body diagram of the nail. What Isaac Newton figured out was that a single isolated force couldn't exist, but that forces in nature always exist in pairs. According to Newton, as the nail is driven into the block by the force exerted by the hammer, which here we have force of the hammer on the nail, the hammer is slowed down and stopped by a force exerted by the nail. Here's the free body diagram of the hammer, and here we have the force of the nail by the hammer. The two forces do not cancel each other out because they are on two different objects. Which is the action force and which is the reaction force? Well, it doesn't really matter. It depends on your point of view. Let's summarize Newton's laws of motion. Newton's first law of motion is also known as the law of inertia. It says that if an object is in equilibrium, which means that the sum of the forces equals 0, then the velocity will remain constant. Newton's second law of motion tells us what happens when the object is not in equilibrium. It tells us that the net force on an object is directly proportional to the acceleration. Forces cause acceleration. Acceleration is inversely proportional to the mass. Finally, Newton's third law of motion states that forces always occur in pairs. These are action-reaction forces. Thank you for listening. Don't forget your Cornell notes. Rewind and review as necessary.